Hi, we are the Green Campus Enterprise, and today we'll be presenting on both our aquaponics and waste heat teams. The goal of Green Campus Enterprise is to annually measure the carbon footprint of Michigan Tech and design and implement projects in order to improve the sustainability of campus to reduce this footprint. Our waste heat team objective is to locate sources of usable heat that are currently being wasted to the surrounding environment and instead find methods to capture and utilize this energy in order to lower Michigan Tech's utility spending and carbon emissions. This year, we primarily focused on the chemical science and engineering building HVAC system, looking into sources of waste heat in their air handler units, fume hood exhaust, and chilled water systems. The first piece of air-to-air energy recovery equipment that we looked into was an energy recovery loop, which uses a closed system of a water glycol mixture pumped continuously between two coils in the supply and exhaust streams of the air handler units or exhaust fan systems. This equipment does not have any physical design constraints during installation. However, it's not as efficient compared to other forms of heat recovery and does require an external source of power to run. The second piece of equipment we looked into was an enthalpy wheel, which is capable of capturing both sensible and latent heat with a high heat transfer effectiveness and relatively low air pressure drop. However, this system does require the two air streams to be physically adjacent to one another and can result in cross-contamination. We also have a heat pipe, which utilizes sealed tubes with a small amount of working fluid through a cycle of evaporation, vapor flow, condensation, and capillary action in order to achieve heat transfer. However, this system does not have as high heat transfer effectiveness, but it is able to run without the use of external power. Finally, for water-to-water energy recovery, we looked into a heat recovery chiller, which is installed in parallel with other chillers and exchanges energy between the hot water heating and chilled water piping system, significantly increasing the coefficient of performance for the entire chiller system. However, this heat recovery chiller would only be usable during periods of simultaneous heating and cooling for the building, which would be the shoulder weather months in Houghton, so only about 4 months out of the year would this heat recovery chiller be able to be effective. So looking at our potential energy savings, our enthalpy wheel installed into the air handler units does have the highest potential savings, since that is with our highest airflow and highest heat transfer effectiveness due to that sensible and latent heat transfer. However, Michigan Mechanical Code prohibits the application of energy recovery ventilation systems into hazard exhaust systems, which does apply to the entire HVAC system for the chemical science and engineering building, since we do have hazard exhaust from the labs. However, there is one exception, which is the application of energy recovery equipment that recovers only sensible heat utilizing a coil-type heat exchanger. So for this reason, we are recommending the installation of the energy recovery loop into the ChemSci's air handler units. This is able to reduce our energy by 2.9 million BTUs per hour, which equates to an annual utility savings of $214,000 a year. This is with a relatively low installation cost of $45,000, so we'd have a simple payback period of about 2.5 months. This system would also allow us to reduce our carbon emissions by about 193 kilograms annually. And with that, we will move on to our second project.
We are part of the Green Campus Enterprise and the Aquaponics Team. Aquaponics is an alternative agriculture method that uses a symbiotic relationship between plants, fish, and nitrifying bacteria to grow food in a space and water efficient manner for the entire year. The basic mechanics of an aquaponics system are as follows. Fish produce waste. This waste is converted to nutrients by bacteria, and plants uptake these nutrients to grow, which cleans the water in the system, allowing the fish to live longer and produce more nutrients for the plants to grow. The aquaponics team's mission at Michigan Tech is to design and build aquaponics systems on campus to use in community outreach and as educational tools about sustainable agriculture, engineering design, biology, and nutrient cycles. The team is currently working on 3 projects. The primary focus of the past 2 years has been designing and building an aquaponics system in the bubble greenhouse, which will be completed this semester. Additionally, a second system looking to be built in the Dow Lab 218 is in the design phase, and the team is consulting a local organization called Kiwanis Cape on building their own aquaponics system. The Bubble Greenhouse project is built as an educational tool, displaying engineering design principles and biological cycles. This system takes up roughly 66 square feet, has a 400-gallon fish tank, and solid waste filters. Last semester, we began consulting with the Kiwanis Community Alliance for Progressive Education. Director Susan Nielsen would like to implement an educational aquaponics system to teach our students about sustainability and healthy eating. We are continuing to move forward and make plans for project build dates starting in the summer of 2025. This semester we begin working on an aquaponics system for the Dow 218 lab. The goal for this is two side-by-side 200-gallon systems used for experiments. Our plan is to use vertical racks with grow beds on top and fish tank and sump tanks on the bottom using a raft NFT system where the beds are on a slant allowing the water to flow using gravity.